Okay, so right here, is this going to be a good depiction of the atom?
No,
Why not?
because you can't really see much of anything.
What do you think might be wrong about this? Because I see a bunch of right, but what do you think might be wrong?
It's not an electron clouds, just electron orbit lines.
Well, there's not actual lines like highways for the electrons to travel around. We know where they are possibly going to be, but we can't know specifically where an electron is at. What's wrong with the nucleus right here? You may remember the two subatomic particles that are going to be in the nucleus.
The proton and the the neutron.
Proton and neutron, so it shouldn't be a one solid little sphere. Now this is actually not a bad depiction. It's actually a fairly decent depiction. It's just know that the nucleus is not one solid little sphere. You do have protons and you do have neutrons. All right, so let's talk about atoms. Okay, so guys, first of all, what is an atom? An atom is going to be the smallest particle of matter that we can still call that element. It's going to have all the properties of that element. So if I talk about gold, I can talk about how a gold atom is still going to have this flammability, this melting point, yada, yada, yada. It's still going to have the same properties of that atom. I can't break it down any further and still possess all of those same qualities. Now, can we break an atom down into smaller pieces?
Yes.
We do now know that you can, protons, neutrons, and electrons. All right, but at the time that they started developing all of this, they thought the atom was the smallest unit of matter, and really it is that will still have the properties of that element. Okay, and we also say that all matter is made up of atoms. This desktop, the legs of the desk, the air that we breathe, they're all made up of atoms. So the early Greeks thought there were 4 elements: earth, wind, fire, and water. Nowadays, we know there's a whole lot of elements. They're all on the periodic table. So let's start talking about the early Greek philosophers. That's the very first person that we will end up talking about. So the first person is going to be Mr. Democritus. So this is the development of, okay, how did we know what an atom was? And how did we come up with the rules about the atom and knowledge of the atom if we can't see an atom? All right, so Democritus was a Greek philosopher. Guys, look at the date, 4 BC. So he was a Greek philosopher, and basically they didn't even have books really back then. They had scrolls that they could write on, and they would sit around and they would think and think and think. I mean, this was the beginning of the books. This was, but we didn't have TV, we didn't have internet, we didn't have phone. But they sit along and they would just think all day long. He's like, hey, if I want to build this desk, I need a desktop, I need legs, I need pieces for that chair. So if I want to build something, I need the building blocks to build it. He goes, I bet it's not any different if I'm talking about just the desktop itself. I bet there's tiny little building blocks in there that we just can't see. And he called those little building blocks atomos. Atomos is the Greek word that means you cannot divide it down anymore. It just means the smallest amount, the smallest unit. And so he called these little invisible units atomos. And now he said, he came up with some rules about atoms as he was sitting there and he was just pondering and thinking and thinking and thinking. He said, hey, all matter is going to be made up of these atoms. He said it's going to be mostly empty space. Like they thought this air that we breathe now, they thought that was just empty space, that there wasn't anything there because you couldn't see it. Now I can see the desktop, so he said there must be something that combines together to make that desktop. That's where he came up with these ideas about atoms. He said the atoms are going to be different on their size and shape and movement. Like atoms of gold are going to look different from atoms of silver. So they're going to look a little bit different. That's what gives different substances different properties. He said, now I can change like how they're paired together to make different substances. Like he said, water must have certain atoms put together, and those are going to be different on their arrangement than what that desktop is. He said that desktop would have different atoms put together differently. So guys, this is very astute thinking for back then. And all it was is because he sat and he thought all day. He was, what makes this up? Now, a year later, we have Aristotle who comes along. So Democritus says, hey, we have atoms. And Aristotle, he was a living God. And by golly, whatever Aristotle said, that was the law. And that's what everybody believed. And so they went to Aristotle and they were like, hey, Aristotle, did you hear what Democritus said? He said, we're made up of these little building blocks called atoms. What do you think about that? And he sat and he thought, and he thought, and he thought. He goes, nuh-uh, that's just silly. He goes, we're not made up of little building blocks. We're not made of atomos. He goes, we are who we are just because we're us. We're not made up of building blocks. No, atoms, that's not right. That's not, that, no. We're not made up of that. And guys, because he was a living God, everybody believed him because, you know, that God spoke through him. And so they believed him for a long time. Can you guess how long they believed Aristotle? And how Aristotle's philosophy, Aristotle's viewpoints changed the science world.
Till he died?
1,800 years. Until somebody else came along and said, hey, you know what? I think we have something small called atoms. Because 1,800 years, he put a block on science because everybody believed him. He was a living God. And so nobody even questioned it. And then we went through the dark times, you know, the dark ages and medieval times. And so finally, with the Enlightenment, we started having the alchemists that were starting to do all the different things, experimentation. Guys, it took 1,800 years before anybody else mentioned anything about atoms. And it was Mr. John Dalton. He was an English school teacher. Guys, look at the year, 1808. 1,800 years later, finally, an English school teacher. Again, no TV, no telephone, no telegraph. They had a lot of free time on their hands. They would read books, they would go for walks, and they would just sit and think and think and think. And John Dalton was like, you know what? He read one of the books about, you know, what Democritus and Aristotle had said. He goes, you know what? I really do think Democritus was right. He goes, we have to be made up of something. Because the only thing that makes sense is that we need to be made up of something. And he came up with 5 rules about the atom. And so he said, hey, every element is made up of these tiny little atoms. He said, we can't break them apart. They can't be broken any further. This is the smallest unit ever. He said, atoms of gold are all going to look the same. Atoms of silver are all going to look the same. He said, we cannot create or destroy those atoms. He said, they're just there. We can't just make poof and have them appear. We can't just destroy them. He said, they're going to combine in specific ratios to form compounds. Like with water. What is our formula for water?
H2O.
For every 2 hydrogens, you have 1 oxygen. He said that's a specific ratio. If I change it for H2O2, you know, 2 hydrogens for every 2 oxygens, now that's peroxide, hydrogen peroxide. He said, so they will change if I change the ratio. I have a new compound that I will be talking about. He said basically, a chemical reaction is going to be where I take and I rearrange those rearrange those elements and what's holding them together. That's what a chemical reaction is. Guys, I'm sorry, this right here, almost all of these 5 rules are 100%, almost all of them are 100% accurate. This is great, great, great thinking. And he wasn't even a scientist. But he came up with the 5 rules. Guys, we call this the atomic theory. I will ask several questions about that on your test. This is the atomic theory. All right, but the problem was some of these statements were not correct. And so let's look at the first one. Dalton said atoms of a given element are going to be identical in size and mass and other properties. Guys, we now know that that is not correct because we now know that an atom's not the smallest thing. What's even smaller than an atom?
Proton.
Proton, neutron, electron. Those are called subatomic particles. Now, we now know about those, and we're going to talk about their development in just a second. Not the development, but their how people found out what they were. Now, I can change my numbers of electrons and my numbers of neutrons. Guys, that leads us into something called an ion or an isotope. This is what we're going to be talking about over the next couple of days. If I change the numbers of neutrons, I have an isotope. If I change the numbers of electrons, now I have a charge that's going to lead us into bonding, and that is something called an ion. And so we now know that, hey, like carbon 12, carbon 13, carbon 14, they're all carbon, but they have different masses. That means the numbers of neutrons change. They are isotopes of one another. So we do know they can be slightly different. As long as the numbers of protons are the same, then we have that element. But if I change the number of protons, my atomic number changes, and I have a new element. And so they are going to have a lot of the same characteristics, but I can have different properties. Not all gold's going to look the same. Not all silver's going to look the same. Not all carbon's going to look the same. They are going to be slightly different varieties of each of those elements. And that's the way it goes for almost every element on that periodic table. They can be slightly different from one another. So that's one thing that he said that was not quite 100% right. Another thing that he said was that atoms cannot be subdivided, broken apart. They can't be created. They can't be destroyed. And guys, I'm going to tell you that statement is true almost 99% of the time. The only time that it is not is when we have a nuclear reaction. I would highlight that. The only time it is not is when we have a nuclear reaction. Okay. Guys, I can actually break an atom open. I can split an atom in half. That is the nuclear reaction we have here on Earth. That's what our nuclear power plants use. I can take an atom and I can break it in half, or I can break it into two new atoms. I can separate them, and whenever they do, it releases a lot of energy, and that's how nuclear power plants work. That's how nuclear bombs work. So that is nuclear fission. Okay, nuclear fusion is what we have on the sun, and we just can't do it here. But nuclear fusion is where you take two different atoms and I smash them together to make one larger atom. Now that releases even more energy. Did y'all ever see the Spider-Man movie with Doc Ock? And he's sitting there and he's like trying to hold that like sun-like orbital. It was such a big joy. He's like, I have created fusion on Earth. Because we can't do that here. We can't take two atoms and smash them together and have a nice stable thing. It's a great nuclear reaction. It releases tons and tons of energy. We can't do that here on Earth. But that's creating new atoms. Or if I take one and I break it into smaller pieces, that's destroying an atom. Or subdividing an atom. Sorry. So technically that statement is true most of the time. But there is that one little chance that it could be a nuclear reaction and I actually do create or destroy an atom. So most of what Dalton said was actually true. So let's recap really fast. Who said we have atoms? Democritus. Who said, no we don't?
Aristotle.
1800 years later, English school teacher, John Dalton said, hey, he was actually right. And he came up with 5 rules about the atoms. All right, so now, hey, we all agree. We have atoms. It's universal. Everybody all agreed. Yes, we do have atoms. Hey, this is a multiple choice question that you might see similar to things that you might see on your test. It says, which of the following is true? So you're going to have more than one. Which of the following is going to be true about Dalton's theory? Is it that elements are made up of tiny particles called atoms? True or false? True. It says all atoms of a given element are identical.
False.
That one is false because you can change the numbers of neutrons or electrons to make ions and isotopes. A given compound always has the same numbers and types of atoms. So water is always going to be 2 hydrogens for 1 oxygen. True. That is a true statement. And what about the last one? Atoms are indestructible.
False.
That's true most of the time, but when is it not true?
Nuclear reaction.
During a nuclear reaction. Or if we have like a collider. And I'll talk about that on the next little chapter that we're going to go over. We can actually smash them into one another to see what these particles are, how they work, how they interact in something called like the LHC, the Large Hadron Collider. All right, so 1 and 3 are the true statements. And I don't know, whenever I downloaded this the other day, it changed where the boxes are. It's really supposed to be 1 and 3. All right, so let's talk about our next person. Okay, our next person, 1869. His name is Dmitry Mendeleev. And guys, he is a Russian chemist right here. Okay, so guys, 1869. We had telegraph at that point, but it was still hard to talk to people across the world and to know what was going on. So people on one side of the world had figured out all these elements, and people over here on the other side of the world had discovered other elements, and it was slow trying to get information back and forth. And so we were saying, oh yeah, this guy, he discovered such and such all the way across the world, and it works like this and this and this. And guys, people were just exchanging information all the time, and it just got to be too much. They discovered so many elements that they're trying to keep in their mind. Okay, well, what about this one versus this one and this one? He goes, you know what? I got to organize this right quick. And so he started looking at some of these different elements, and he started grouping them by their atomic mass. Highlight that. He started arranging them by their atomic mass. Now, as he was doing this, he realized, oh, hey, these right here, they all like react with water. And so he put all the ones that react a certain way kind of in a column. And he still had it arranged by their atomic mass. He said, hey, these right here, they're found more in like the Earth crust. And so he started noticing patterns. And so he was able to place them all out by their atomic mass, but then also group them versus certain characteristics or certain traits. And when he did that, he noticed that there were blanks in the periodic table. This is Mendeleev's actual periodic table. He noticed that there were blanks here. And so he's like, oh, hey, there must be something out there still that has a mass somewhere around this, but it acts this way. And so based off of that, since I know some of the characteristics, certain scientists were able to go out and start looking and searching for those different elements that were missing. So Mendeleev, very first periodic table, arranged by the atomic mass. All right, so now let's get back to talking about the atom. Let's talk about those subatomic particles, because of Dalton, we know we have an atom. So again, recap. What did Democritus say?
There are atoms.
We have atoms. Aristotle?
No.
No, we don't. Dalton? Yes, we do.
Plus 5 rules.
And then, in his 5 rules, atomic theory, and then Mendeleev arranged the periodic table based off of their
Atomic
mass. Okay, so now let's start talking about the atom with those subatomic particles. The very first one we're going to talk about is Mr. J.J. Thomson. Guys, look at that, 1890. So England had a lot of really good scientists. I mean, all of Europe. England, Germany, France, all of that has some great scientists. Okay, so let's talk about J.J. Thomson. Guys, right here, he used something called the cathode ray tube. All right, so the cathode ray tube, it was this little glass tube that was filled up with gases that were going to shoot electricity through it. We talked about this the other day. Basically, it was making like a plasma on the inside. But you can see the little line going across the tube as he applied electricity to it. There's an electrode at each end. And so he started playing around with it. And he used that with a magnet. And he found, here, I'm going to show you a picture of it really fast. This is what it looks like right here. He realized that if he put a magnet up beside it, because you just had this green line, he realized that if I put the positive side of a magnet beside it, it went upwards. But if he flipped the magnet over and he put the negative side next to this tube, the line went downwards. So he was like, well, this is odd. Why is that happening? Have you heard the phrase opposites attract?
Yeah.
So if I put the positive side of a magnet next to it and it goes upward, what does it tell me about the charge of that line? Negative. It's negative. When you flipped it over, you put the negative part of the magnet, it deflected it downward. And so he shows, hey, there's some type of charge on this line. And so that's what led him to realize that there are certain parts of the atom that have a negative charge. And that's how we discovered the electron, was with a cathode ray tube just like this. Now, we use those cathode ray tubes in TVs. Have you ever heard the phrase, hey, I'm just going to go watch the tube? You don't really hear it much anymore because now we have plasma TVs, we've got LED TVs, but used to, the old TVs, the original ones, had a tube just like this. And that's what helped to produce your different light with the pictures. All right. So, because of him, we now know that, hey, we have something negative in the atom. And if we have something negative, that means we must also
have something positive.
Have something positive. Because Dalton, think about Dalton really fast. Think back to Dalton. He came up with the 5 rules about the atom. He thought the atom was a solid sphere. Kind of like a bouncy ball. He thought it was just a solid sphere. Nothing else to it. It was just neutral. Well, now because of J.J. Thomson, we said, hey, we've got negative charges somewhere in here. So we call J.J. Thomson's model of the atom the plum pudding model. Or you might also hear it called the chocolate chip cookie dough model, chocolate chip cookie model. Basically, if I had a scoop of chocolate chip cookie dough, if y'all all played with chocolate chip cookie dough, right? You roll it up into a ball. He basically said those electrons are going to be just like the chocolate chips spread throughout that ball of cookie dough. He said it's still going to be a round, like ball kind of shape. It's solid. He said now the dough itself is probably going to have a positive charge because if I have negatives, I must also have positives. That way we have a neutral atom. So this area right here is supposed to be positive. These are the negative electrons studded throughout it. Now, he came up with this in the 1800s, and they didn't really have chocolate chip cookies like this back in the 1800s. So back at that time, they called this the plum pudding model. Basically, plum pudding is kind of like raisin bread. Have y'all had raisin bread?
Yes.
It's similar to that. And so you have like this big mound of dough, and inside of it you have all these little raisins spread in it. So it's kind of similar to like a chocolate chip dough. But that's what we call it. So we have negative electrons in a positive region, but we still thought it was just one solid sphere. All right, so J.J. Thomson, cathode ray tube, and chocolate chip cookie dough, or plum pudding model. Okay, so hey, we have electrons. Now we want to learn about those electrons. We want to know everything about the electrons. So remember, this was in 1890. So a couple of years later, the next guy came along. Look, 1909. So it took almost 20 years for us to learn more about the electron. And so this one is Robert Millikan. Okay, so Robert Millikan, he used an oil drop apparatus. That was the name of his experiment, the oil drop apparatus. And it was really kind of cool. This is what it looks like. And so this is an inside kind of drawing of it. This right here, it's like the old-timey perfume bottles where you spray the little bulb and it turns the perfume into mist. Well, he put oil inside of here. And whenever he squeezed the little bulb, it turned that oil into a really, really fine mist. Now, inside this chamber, you have this little plate that has a little hole on it. Well, because of gravity, what should happen to all that oil?
It should fall down.
It should fall right through that hole and start falling all the way down. But he charged these two plates. They have electricity hooked up to them. And he could adjust the electrical current going in and out of the plates. And as that oil drop was falling, he could change the electrical charge on these plates where he'd slow down that drop. He's like, oh, that's kind of cool. And then he could adjust that charge a little bit more, and he could actually make that charge go up against the flow of gravity. He could actually make it go upwards. And he could adjust the plates a little bit more, and he could make that oil drop just hang in midair. It was just sitting there, just suspended in midair. And once he knew what those two charges were that caused that oil to just sit hanging in midair, he was able to take those numbers, plug it into this big long equation that you don't have to know. Basically, he was able to figure out the mass and the charge of the electron because of this oil drop apparatus. So he determined the mass along with the charge of the electron. So the way I remember him, I told you I was going to give you all some anagrams. If I drive down Knickerbocker, there's a place called Meineke that changes your oil. They do oil changes. So Millikan sounds kind of like Meineke. I know it's kind of goofy and it's a stretch, but Millikan sounds a lot like Meineke. So Millikan, Meineke, oil drop, mass and charge of the electron. So he has the Millikan, Meineke, oil drop, mass and charge of the electron. Everybody do it with me. Millikan, Meineke, oil drop, mass and charge of the electron. So Thomson figured out, hey, we have electrons. He now figured out the mass and the charge of electrons. And basically said, look, that's the negative 31. That's such a small, minuscule mass. We say, hey, the mass of that atom is not coming from the electron. It's coming from something else inside the atom. And so we can say, hey, so tiny and so minuscule, we don't even have to worry about it. So let's just recap the study of the electron. So J.J. Thomson, cathode ray tube, said, hey, we have negatively charged. If you have negative, you also have positive charges. He came up with the plum pudding model. Again, solid sphere, just dotted with all these negative electrons. And then Millikan, Meineke, oil drop, mass in charge of the electron. And so he said the atoms have such a small, or the electrons have such a small mass that they do not make up the mass of the atom. Something else must be in it, the positive region, that's giving all of the mass. Okay, so I do throw Marie Curie in right here, because her experiment and her discoveries are what led to the next experiment. So Marie Curie, radioactivity. So Marie Curie was the one who discovered radioactive substances. So let me tell you a little history about her. And I'm going to tell you right now, I am definitely not a feminist. But I do want to touch on her for just one moment because she was outstanding. Guys, look at whenever she did her discovery. She was born and raised in the 1800s. And I don't know if you know a whole lot about females back in that time period, but basically you did not have jobs. Your whole goal was to cook, clean, keep the house clean, raise your kids. You didn't have jobs outside of the home. Females didn't go to school really. And so you might have, an education up until like 4th, 5th, maybe 6th grade. But after that, you didn't go on to college or anything else. Very few females did. Well, fortunately, her father had 2 girls, and he did not want them basically being that dependent on a man. He didn't want them having to just be stuck at home because he saw how smart, how brilliant they were. So he hired private tutors to come in and teach them. And oh my gosh, everything that they were given, they got it. It was so easy for them. And so they were fantastic students. So he was like, you know what, you really do need to go on to college. You like all this chemistry and physics and math and science education, you need to go on. So she applied to several different places, and finally one of them said, hey, we'll let you come. It was called the École Polytechnique. It was in Paris, France. It was got one of the leading colleges, universities at that time. They're like, hey, you are a really brilliant student. We'll go ahead and let you come. However, we don't want you to distract the guys. Because they really did think a female walking around in the same building as them was going to distract the guys. They're like, hey, we'll let you come, but we'll give you an office. You have to stay inside that office. You're not allowed to get out of it. And when I say office, it was a tiny little closet, like 4 of these desks put together. It was a tiny, tiny little closet. She couldn't go to the lectures. She couldn't do anything. She couldn't do her labs. The professors would bring her all of her stuff. She'd sit there and do all of the work. She had to wait until the end of the day when all the men had left before she could come out and actually do her experiments. And so there was a professor that was watching, and he was like, hey, everything we give her, she's doing so much better than all the guys. She's like an amazing student, and she's like having to live up here almost because she has to wait till the guys go home before she can come out and do any of her experiments. He goes, this just isn't right. So he walked up to her and said, hey, I have a lab over here. It's my research lab. Nobody is in there. You're not going to distract anybody. Go do your stuff in there. That way you're not here all the time. And guess what his name was? Pierre Curie. And so that's how they met. They fell in love. They got married. They had a couple of kids, 2 daughters. And they discovered radiation together. And they named it, one of the substances, one of the elements that they discovered, they named radium. So they both got a Nobel Prize for it. Now, unfortunately, their love story came to an end pretty quickly because he got killed in a hit and run by a horse-drawn carriage. Can you imagine the pain that would be? And so she went on. She still discovered several other different things like polonium. She named this after her home country, Poland. She ended up with a couple more Nobel Prizes. She became one of France's top scientists. So she was buried in one of their big cathedrals there. Guys, her body had so much radiation in it because they didn't realize radiation was harmful. She ended up dying later on from a cancer called leukemia. And it was a very painful, horrible death because they didn't realize the dangers of all the radiation being absorbed into her body. So her lab was very, very radioactive. They had to completely do a scrub down of her lab to try to get some of the radiation out. Her lab notebook was very radioactive. You can still go into her lab and see her lab notebook now. It's under a heavy plate glass because of how radioactive it still is. Really, the only way to stop radiation is through lead. So when she was buried, her body had so much radiation, it was emitting all these particles, because that's what radiation is. It's just these little particles that come out from the atom. They just didn't know what those particles were at the time, but it's releasing particles. Her body was so radioactive that they had to line her casket in lead to try to keep everything safe. All right, so because of her experimentation, it allowed this guy to do his experiments. So this guy, his name is Mr. Ernest Rutherford. He did something called the gold foil experiment. So a way to remember him, can y'all roll y'all's R's? Can y'all do? You might need to know Spanish. You need to be able to roll your R's. All right, so a student told me this one. They're like, hey, Miss Rutherford, he did the gold foil. So Rutherford, rich, the gold foil experiment. Everybody try to do that with me. Rutherford, rich, gold foil. Oh, y'all aren't even going to try, are y'all? All right, so basically, he took this piece of gold foil, and they thought atoms were solid spheres, so one right next to another, next to another. If I shine a light on this desktop, what's it going to do? It's going to bounce back, isn't it?
Oh.
Well, he thought the same thing. If this was solid, those atoms should be right next to one another. If I shine some particles from radiation past it, then they should go right on through. Hey, by the way, on Marie Curie, some of that radiation, guys, they used it about 10 years later 15 years later in World War I. They made the very first X-rays. That's why she was able to get another Nobel Prize, because they used that radiation. The radiation should have gone right through the tissues of people's bones, and they were able to capture the radiation with a special film to make X-rays. And it was really big work, because about 30, 40 years before, whenever we had the Civil War, if you had broken bones that were horribly, horribly broken, if you had bullets lodged in you, they had to cut off your legs. Well, during World War I, they were able to save all these different limbs off of people because of that radiation. All right, so basically his thought was kind of like that X-ray technology. If I shoot some of those particles through this gold foil, they should bounce right back. But when he started this, all those particles went right through the gold foil, and right through it, and right through it, and right through it. So he was like, hey, there must be empty space in between these different atoms. He was like, the atom must have a lot of empty space. Because up to this point, we thought the atom was still a solid sphere. He was the first one that realized, oh no, there's a lot of empty space in an atom. And so he sat some research students sitting here watching this for months and months and months at a time. And occasionally, one would bounce back. So we realized there must be something inside that atom. It's really tiny, but something really hard and dense that occasionally one of those radiation particles will hit it and bounce backwards. But most of the time, there's a lot of empty space in atoms. So most of the time, those particles are going to go right past the atoms through that empty space. So he said, first one, the atom is not a solid sphere. It has a lot of empty space. He said that empty space is where the electrons are at. In the middle is a positive region called the nucleus. And so this is what he thought the atom looked like. We're getting better now. So we said the electrons were circling around. We said the nucleus is the positive region. All right, so basically, if I were to take the atom, you've all been to San Angelo Stadium over on Knickerbocker, right?
Yes, ma'am.
All right, he said basically, the nucleus is the size of a marble. And if I looked over to the 50-yard line and put that marble down, that would be the size of the nucleus in comparison to the rest of the atom. Most of it was empty space. So if I'm shooting particles at it, it's going to go right on through, right on through, right on through, right on through almost all of the time. But occasionally we're going to get lucky, and one of those radiation particles is going to hit that little marble on that 50-yard line and bounce backwards. And so that's how they were able to figure out, hey, the atom is mostly empty space. Now he said that nucleus is where all of the weight is at, because those electrons, remember from Millikan, we said weigh nothing. So all of the weight is in the middle, in that nucleus. Okay, so Rutherford, rich, gold foil. All right, so now let's talk about Mr. Moseley here. Moseley, guys, I'm sorry, he could have rivaled Einstein. He died when he was like 24, 25. He discovered a couple of different elements. He perfected some of our different equations. He actually took Mendeleev's periodic table and said, hey, there's some problems here, there's some discrepancies. We've now figured out more elements. You know what? Let's arrange it by the atomic number, because now we knew about protons. And so highlight that. He arranged it by the atomic number. Guys, that right there on the board, that on the wall is Moseley's periodic table. We still use it to this day. So the two M's, Mendeleev, Moseley. Look over here. M-E comes before M-O. Mendeleev did it first. Moseley did it last. So alphabetical order. Mendeleev did it by the mass. Moseley did by the atomic number. Those are test questions. So the two M's, Mendeleev, Moseley did the periodic table. Guys, he would have been a superstar. He would have rivaled Einstein. However, World War I started. He was drafted, given a gun, put on the front lines. Unfortunately, an Italian sniper picked him off. And so we don't know what we lost. We don't know what he could have done. Because he was early 20s when he did all of this stuff. He would have rivaled Einstein. And he was an American. Guys, it is because of him to this day that scientists are not allowed on the front lines. If you're a scientist, you're in the lab. You're developing new technologies. You're perfecting things. But they do not allow scientists on the front lines because of him. So, and then I feel sorry for this guy. His name is James Chadwick. He invented the nucleus. I don't have a story about him. Not invented. He discovered the nucleus. So it's quite a bit later. Just know he discovered the nucleus. So now we have all three subatomic particles: protons, neutrons, and electrons. All right. So this is what it looks like now. Protons and neutrons in the middle in the nucleus. Electrons are on the outside. So Rutherford said it had a lot of empty space. Before Rutherford, we thought it was a solid sphere. But now we've perfected it, and we keep perfecting it. All right. So I want everybody right now, take a big old breath of air. Go. Release. In that breath of air, you breathed in a lot of different atoms. Some carbon dioxide, some carbon monoxide, oxygen. Do you know that the air that you just breathed in, Stetson just breathed out? And so all that air that he just breathed out was just touching the inside of your lungs. Because we recycle all these different atoms. They've been around. We can't create or destroy. Remember, that was something that we just said. The only time we can is during nuclear reactions. We can recombine them with other elements, make new products like your carbon monoxide versus carbon dioxide. But they have been around since like dinosaur time. Some of those atoms you just breathed in, because air circles the globe. At one time, some of those atoms touched the lungs of dinosaurs. And it's kind of cool to think that. You know, some of those atoms that you just breathed in at one point touched the lungs of like JFK. But then in hindsight, some of those atoms you just breathed in also just touched the lungs of people like Adolf Hitler. Because we recycle these. All right. That's it for today.
Video.